Hi, welcome to Proficiency Eagle Series Online. My name is Philip Liang, one of the tutor at Proficiency Education's Eagle class. In order to state rank and come first in the state, getting a raw mark of 100% is sometimes not enough. In this series of videos, I will be posting 4-unit challenge questions weekly, focusing more on how the examiners compare the answers if both students attain full marks. It's recommended that you try these questions yourselves and time yourself before going through the answers. So today we'll be doing a complex polynomial question. So we're given this polynomial pz, and we want to prove this inequality that has beta in it. So we know that beta is a root, so we want to sub it in because it will be equal to 0, and also because the solution has beta in it as well. So we want to try and match our solution, the equation we have with the answer. So we see that beta n is moved over to one side. So we want to try and copy that. And also that they take the modulus of everything inside. So we can do that too. So we just simplify. And we notice that here the modulus is around the entire expression, whereas in the answer it's only on individual expressions. So if we recall, there's a proof called the polygonal inequality, where we can separate all of these, just like triangle inequality. And the reasoning would be polygonal inequality. And again, we just simplify a little bit more. We take out each individual component. And finally, because we're given that m is the maximum value of all the coefficients, we can say that m is bigger than or equal to all of these coefficients. And therefore, we can simply replace it and it will be bigger. And we can factorize it as well. And that's that question. So moving on to the next part, we want to try and prove this new inequality. So one logical step would be to take the geometric sum of this expression here, because we want to get rid of all those terms. So from part 1, we can do a geometric sum. The first term is 1, beta is the ratio, and there's n terms. So we can write our reasoning, geometric sum. And one logical step would be to move this over to the left-hand side. But there is one important condition when we move that over. And that is that beta minus 1 must be greater than 0. Because if it was less than 0, the sign would change. So keep in mind that for this to be true, beta must be greater than 1. And this will come into importance later on. So we want to try and just manipulate this, so we emulate the answer. So we want a 1 plus m somewhere, right? So we can try and factorize and see where to go from there. So I get this. I can divide it by beta to the n, and beta to the n, the modulus is definitely greater than 0, so the sign won't change. And we reach this final step. So we know that m and modulus of beta are greater than 0. Therefore, m over modulus of beta to the n is also greater than 0. So the last step to this would be to just completely remove it, because this is bigger than 0. So therefore, m plus 1 is larger than beta. But keep in mind, this is for beta is greater than 1 so far. So to finish this question, because this is true for any beta, we must prove that this is also true for beta greater than 0 and less than or equal to 1. So this is actually pretty simple because, again, remember that because m is greater than 0, if we add m to the right-hand side, it will just be bigger, correct? 1 would be less than 1 plus m, and therefore beta, modulus of beta would be less than 1 plus m. And therefore, we've proven it for all beta. And that's how you do the second part. Okay, so for the last part of this question, we're given a new polynomial Sx with all these conditions, and we want to prove that Sx equals 0 has no real solutions. So we want to try and relate this to the first polynomial that we're given, pz, and we want to write it in a similar fashion, so in sigma notation. So referring back to the first part, we get this. And one key important information is that pz is a monic polynomial. Therefore, an is equal to 1, and that will be very useful later. So the similarities between pz and sx are quite a lot, but the difference is z and x plus 1 on x. So what we can do is we can sub z equals to x plus 1 on x for sx. And we produced a new equation, sz equals to n z to the k. And this is even more similar to pz. So for these type of questions, one method of proof is proof by contradiction, where we assume the opposite and then we find a clear contradiction. So to start it off, we can assume that Sx equals 0 has real solutions. And we can let that solution be z equals to beta. So the reason why I can let z equals beta is because even if Sx has a real solution, I mean x is a real number, so we can sub it in here, and z must also be a real number too. So we can sub in beta to sz. And remember how I said that pz was a monic equation? So we want to try and emulate that in our new equation, polynomial, because we want to use the result of the previous part, ii. So currently, the coefficient of beta to the n is cn. So to make it polynomial, we must divide it by, well, cn. And, well, cn over cn is equal to 1. So it is a monic polynomial now. Moving on, remember that we were given this condition, ck is less than cn, the magnitudes. So since we moved it over, it's now ck over cn. It is now less than 1. So therefore, the maximum value of all the coefficients in this particular polynomial, it must be 1. In other words, m is equal to 1. So if we use our results from part 2, we can sub m into part 2, 1 plus 1 from part 2, and therefore modulus of beta is less than 2. But since we're doing a proof by contradiction, we want to try and somehow prove the opposite as well. And we want to try and prove that using this substitution we used, z equals x plus 1 and x. So required to prove that modulus of beta, which is also modulus of x plus 1 and x, is actually greater than or equal to 2. So this is a common inequality. And one way of doing this inequality is you can work backwards. So I'll just write from the bottom and work my way upwards. So I can square both sides, expand it, and finally we reach a point which is clearly true. So I work backwards, but in the exam paper, it seems like I'm working forwards because you can't assume the answer. So after all of this, we prove that finally beta, modulus of beta, is greater than or equal to 2. But we also prove that modulus of beta is less than 2. So there is a clear contradiction between these two points. So therefore, there's a contradiction. So your assumption is wrong. And what was our assumption? Our assumption was that Sx equals 0 has real solutions. Therefore, Sx equals 0 has no real solutions. And that's how you do that question.